The International Space Station is a laboratory that orbits the Earth once every 90 minutes. It's the most expensive single project ever constructed. Jointly owned and operated by the United States, Russia, Europe, Japan and Canada, the ISS is a triumph of international collaboration. But it didn't start that way. And during its planning phase, it came close to being dumped.
Tonight, I am directing NASA to develop a permanently manned space station and to do it within a decade.
It was 1984, toward the end of the Cold War, when President Ronald Reagan unveiled his plan before the Congress. It was soon called Space Station Freedom, but details were sketchy and plans kept changing. NASA saw a space station as their next logical step. The Space Shuttle had been designed with on-orbit construction as one of its primary functions. On a cold morning in January 1986, the Space Shuttle Challenger was being prepared for its 10th flight.
And liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Challenger, go with throttle up.
Challenger, go with throttle up.
All 7 astronauts were killed, and the shuttle program was suspended. Just 1 month later, cosmonauts began occupation of Mir, the new Soviet space station. The Soviet Union had a long-standing interest in extended duration space flights with its Salyut space stations. And with Mir, the Russians were gaining valuable experience in microgravity research and on-orbit construction. As the 80s progressed, Mir expanded using modular fabrication techniques. They began experimentation with automated docking systems. New modules were delivered by the Proton launcher with the Progress cargo ship used for resupply. NASA's shuttle fleet remained grounded, while an exhaustive inquiry was conducted, and Space Station Freedom was stuck on the drawing board. In 1989, discontent in Poland spread across the Eastern Bloc, leading to the fall of the wall that had divided Germany. 2 years later, the Soviet Union itself was dissolved, followed by social and economic turmoil. Moscow was now the capital of the Russian Federation, a one-party democracy. The Mir crew EO-10 arrived at the space station as Soviet citizens and would return to the ground as Russians. The country's new space agency, Roscosmos, had had its budget slashed by 80%, and there was no money to launch 2 newly completed modules. In 1988, NASA had resumed shuttle flights. But with the fall of the Soviet Union, interest among US politicians in Space Station Freedom was at an all-time low.
Roger, roll, Discovery.
NASA now began working with Roscosmos. In the Shuttle Mir program, the Russians would benefit from an injection of badly needed funds, and the Americans would gain expertise in long-duration spaceflight. Astronauts learned Russian and began riding to orbit in the Soyuz. Cosmonauts learned English. During the program, 10 cosmonauts flew on the space shuttle, and 8 Americans served as crew members aboard Mir, with the shuttle docking with the Russian space station 9 times. Roscosmos had begun work on a replacement Mir 2 project, completing the functional cargo block and the DOS-8 habitation module, but lack of funding forced the agency to shelve the plan. NASA convinced the cash-strapped Russian Federation to come in on their project. Europe, Japan and Canada were also involved in what was now called the International Space Station. The functional cargo block was renamed Zarya and became the first piece of the International Space Station delivered to orbit in November 1998. Zarya was launched from Kazakhstan with an orbital inclination of around 50 degrees. This set the orbit for the International Space Station. The Space Shuttle would deliver the bulk of the modules from here on. NASA knew that this orbit would give the shuttle problems. Launched from Florida, the shuttle usually orbited at 30 degrees. To reach the steeper inclination with any meaningful payload, the shuttle needed more power, or it had to lose weight. A redesign of the cargo bay delivered some weight savings, but the construction missions could only be achieved with a new external tank made from a new lightweight alloy.
We have a go for main engine start. We have main engine start. 4, 3, 2, 1. We have booster ignition and liftoff of the Space Shuttle Endeavour with the first American element of the
2 weeks after the launch of Zarya, the Space Shuttle Endeavour lifted the Unity node to orbit.
Houston's now controlling. Endeavour's rolling on a course heading northeast from the Kennedy Space Center toward a 240-mile-high rendezvous with the Zarya control module.
In preparation, the crew connected the Unity node to the shuttle's airlock, and using the shuttle's robotic arm, they united the 2 modules. The crew entered the space station for the first time and stowed equipment, but no one would take up residence just yet. Construction work had just started. It was 18 months before the arrival of the next module, Zvezda, the Russian habitation module. It docked automatically with the Zarya module. In October 2000, the Space Shuttle Discovery arrived with more pieces. During 4 spacewalks, the crew installed a structural truss and communications equipment. Finally, in November 2000, the first crew, Expedition 1, launched from Baikonur. Cosmonaut Yuri Gidzenko was commander of the Soyuz spacecraft. Astronaut Bill Shepard was the commander of the team once they were on the International Space Station, and Sergei Krikalev, the most experienced member of the crew, was flight engineer. Much of the crew's daily activity was devoted to the unpacking and installation of equipment. There are always problems that need to be solved and maintenance to be carried out. In microgravity, muscles lose tone. One of the first pieces of equipment to be set up was an exercise bike. Every crew member is required to do 2.5 hours of cardio exertion every day. Unlike later missions, Expedition 1 carried out very little scientific research. At this stage, the station's primary laboratory module was still on the ground. But that would soon change. The crew of the space shuttle Atlantis delivered the laboratory module called Destiny. It was a radical increase in capability for the space station. The laboratory is equipped with 13 international standard payload racks that can house a variety of different experiment modules. But at this stage, they were empty. With the Destiny module and a new, much larger solar array, the International Space Station was taking shape. a precisely organized launch schedule was unfolding, and it was expected that the space station would be complete by 2006. In November of 2002, the Space Shuttle Endeavour took off, carrying the Expedition 6 crew, plus a new piece of the space station's superstructure and 2 tons of supplies. Returning to the ground, no one realized that it would be the last time a cosmonaut would fly on the shuttle, and that construction work on the ISS would be suspended for more than 2 years.
Columbia, Houston, comm check.
When the Space Shuttle Columbia broke up during re-entry to the Earth's atmosphere, all remaining shuttles were grounded.
Columbia, Houston, UHF, comm check.
81 seconds after launch, foam insulation separating from the external tank had damaged the left wing, and from that point, Columbia was doomed. The investigation board had no confidence that the entire Space Shuttle fleet could be safely operated for more than a few years, calling the shuttle an aging spacecraft. With shuttle flights suspended, construction work on the International Space Station stopped. Replacement crews were cut to 2 members. The Russian Progress freighter was the only method of delivering supplies to the ISS, and all crew rotations used the Soyuz spacecraft.
Принято 30 секунд, на борту порядок.
What started out as America's space station freedom was now completely reliant upon Russian technology. It would be more than 3 years before construction work on the space station recommenced. In 2004, US President George Bush made a speech to an assembled group of NASA administrators.
Our first goal is to complete the International Space Station by 2010. In 2010, the Space Shuttle, after nearly 30 years of duty, will be retired from service.
The Space Shuttle would be restricted to work on the International Space Station, where the crew could await rescue if their craft sustained damage. Scientific work was cut to a minimum, with the small crews preoccupied with station maintenance. Fabrication work on the modules continued on the ground. The Space Shuttle Discovery made the return to flight mission in 2005. Before docking with the International Space Station, it performed the rendezvous pitch maneuver, allowing the ISS crew to inspect the craft for damage. It delivered supplies and equipment and returned safely to the ground. Atlantis arrived 14 months later, and after a break of almost 4 years, construction work began again. In what became known to NASA astronauts as the Wall of EVA, that's extravehicular activity, it took 14 more shuttle assembly flights to bring the ISS to its current configuration. If just one of the installation spacewalks was to fail, it could threaten the entire project. The schedule was relentless because the shuttle's days were numbered. Training for these assembly missions was intense. NASA's neutral buoyancy laboratory was rigged with a mock-up of the ISS, so astronauts could experience something akin to weightlessness while they practiced. In July 2011, Atlantis flew to the ISS on what was the final flight of the shuttle fleet. The International Space Station was essentially complete, although it continues to be reconfigured and new pieces can still be added. Its 16 pressurized modules have a volume equivalent to a 5-room house, including laboratories, storage spaces, and habitation areas. Power comes from 8 solar array wings, which track the sun. When the ISS enters the Earth's shadow, the solar wings enter night glider mode, where they are angled edge-on to the orbital direction. Though the ISS orbits 400 kilometers above the Earth's surface, there is enough thin atmosphere at that height to present drag. Night glider mode reduces this drag and minimizes orbital decay. Supplies of water, oxygen, food and equipment are regularly delivered by unmanned cargo craft. Most frequent of these has been the Russian Progress, which is similar in appearance to the Soyuz. It docks by itself using the automated Kurs system. It can also be docked manually if the need should arise. Like the Soyuz capsule, the Progress freighter will remain docked long-term. As well as delivering supplies, it can boost the station's orbit, or it can transfer fuel for the station's thrusters. Ultimately, filled with garbage, it undocks to burn up in the atmosphere. The Japanese space agency, JAXA, currently operates the largest cargo craft that still visits the ISS. To dock with the space station, it approaches in stages until it's close enough to be grabbed by the robotic arm and connected to one of the berths on the Harmony node. It has a pressurized zone that can be unloaded by hand, and there's an unpressurized area, accessed by the robotic arm, for cargo to be stored on pallets outside. With the demise of the space shuttle, NASA has turned to the private sector to fulfill its resupply commitments. The Cygnus freighter first visited the ISS in 2014. The SpaceX Dragon cargo craft first delivered supplies to the ISS in 2012. It is different from the other cargo craft in that it can return significant loads back to the ground. Experimental materials from the ISS can be in an Earth-based laboratory within 2 days of leaving low Earth orbit. SpaceX is developing a Dragon capable of carrying astronauts to low Earth orbit. The business of the International Space Station is research. The study of fluid dynamics and materials science in a microgravity environment simply cannot be done on the ground, and the orbiting platform is the perfect place for Earth observation, meteorological studies, and astronomy. The study of plant development in microgravity is of great interest. One of the major areas of study is into the effects of prolonged weightlessness on the human body. Without the resistance provided by gravity, muscles and bone deteriorate. This is partially offset by regular exercise. The ISS is equipped with a treadmill, a cycle ergometer, and a resistive exercise device. All are shock-mounted so as not to pass vibration across the station. The loss of bone mass shows up as raised calcium levels in the blood. Blood samples are taken regularly and stored at low temperature for later analysis. The extra calcium can lead to kidney stones. NASA and JAXA are cooperating in the study of an agent that can prevent these effects. Most astronauts on long-term missions complain about deterioration in their vision, which can persist for years after a flight. Distinct changes to the eye have been detected, and ultrasound examinations of the eyes are done regularly. Astronauts and cosmonauts are totally reliant upon the technology of the ISS, and it needs regular maintenance. In August 2018, a small but steady drop in air pressure was noticed. It was traced to the Soyuz MS-9 capsule. A 2mm hole appeared to have been deliberately drilled, and nasty rumors about sabotage began to spread. Cosmonaut Sergei Prokopyev made a recording from the Soyuz to show the repairs and to quash stories about poor morale on the space station.
As you see, everything is calm. We're living in harmony as always, and all the experiments are going to plan.
Later, it was decided that a spacewalk to cut away some of the external insulation from the Soyuz above the hull might deliver more clues about how the hull could have been made. Because the Soyuz capsule is not designed for external maintenance and lacks handrails, it was a challenging job for the cosmonauts. It was difficult slicing through the 8 layers of the thermal blanket used to stabilize internal temperatures on the spacecraft. From the inside, it appeared that the hole had been repaired with glue, which gave out after the Soyuz had docked with the ISS. It was thought that analysis of the glue would shed more light on the mystery. Because the hole was in the habitation module, it was no threat to the craft's safe return. The blanket, which was left in a mess, is also not required during re-entry. Russian cosmonaut Sergei Prokopyev, European astronaut Alexander Gerst, and American astronaut Serena Agnon-Chancellor had flown up on this spacecraft and would be returning home on it. When maintenance or repair work has to be done outside the ISS on NASA, ESA or JAXA modules, the crew members with the required expertise have training in the use of the American spacesuit, known as the EMU. Some crew members have training on the EMU and the Russian all-land spacesuit. Those with experience in both say that the American suit is more flexible and comfortable, yet it is very complex and takes a very long time to put on. By contrast, the Russian suit is simple to put on and is designed to be easily serviced by cosmonauts. Even the smallest equipment malfunction can be life-threatening. When ESA astronaut Luca Parmitano was installing cables outside the ISS, water started leaking into his helmet.
I feel a lot of water on the back of my head, but I don't think it's leaked from my back.
Are you sweating? Are you working hard?
I am sweating, but it feels like a lot of water.
Mission Control called him back inside, but by the time he had reached the airlock, he couldn't see and he couldn't hear. His colleagues quickly got him inside and removed his helmet, along with more than a liter of water. Later, the empty suit was powered up and the fault was obvious. The water was leaking from the suit's cooling system. A report blamed Mission Control, who assumed that the water was coming from the in-suit drinking water bag. A crew will typically stay in orbit for around 6 months. The arrival of a new crew means that for 3 other crew members, their stay is coming to an end. They board the same Soyuz craft in which they traveled to orbit for the return to the surface. Undocking of the capsule is precisely timed. It separates initially by the spring mechanism in the docking interface. Only at a safe distance from the ISS will the Soyuz make the first of its separation burns to avoid contaminating the space station. At a point in the orbit opposite to their intended landing area, the retroburn happens, slowing the craft for its descent into the atmosphere. This burn is precisely timed and lasts 4 minutes and 45 seconds. At this stage, the descent capsule is still attached to the habitation and instrument modules. In Kazakhstan, a fleet of ground vehicles are heading for the landing zone. Medical teams and recovery personnel from Roscosmos, NASA and ESA are also in the air. Explosive bolts fire to separate the 3 parts of the Soyuz. During the heat of re-entry, the crew are out of radio contact with the ground. In the upper atmosphere, the drogue chute deploys, further slowing the capsule. And then the main chute. On the ground, the crew are lifted from the capsule. They're experiencing gravity for the first time in months, and it will take them months to return to normal. They are carried through the snow and will soon return to their homes. Jupiter is our solar system's largest planet. It's more than twice the mass of all the other planets combined. Its swirling atmosphere moves in bands at different latitudes, and its great red spot is thought to be a perpetual storm. Recently, images from a new probe that has flown above Jupiter's poles reveal a completely different planet. The ancient Romans knew Jupiter as the celestial representation of the king of the gods. In 1610, Galileo, using his newly improved telescope, saw Jupiter's moons and could see they orbited the planet, evidence that not everything revolved around the Earth as the Church had declared. Though better telescopes improved our view of Jupiter, it was not until 1964 that Gary Flandreau, a graduate student working part-time at NASA's JPL, understood there was a way to get a clearer look at Jupiter. By plotting the positions of the outer planets, he realized that a rare alignment would enable a spacecraft launched in 1977 to visit Jupiter, Saturn, Uranus, and Neptune. NASA jumped at the opportunity and began work on twin craft for what was then known as the Planetary Grand Tour. To limit any surprises, two basic spacecraft, known as Pioneer 10 and 11, were quickly built. They would go ahead of the Grand Tour missions to send back information about the environment. Pioneer 10 was launched toward Jupiter in March 1972. It was the first spacecraft to cross the asteroid belt that lay between Mars and Jupiter, and because it was the first probe on a trajectory that would take it out of the solar system, it carried a plaque identifying its origin. By December 1973, Pioneer 10 was sending back pictures of Jupiter clearer than anything that had been seen before. Approaching Jupiter, it encountered levels of ion radiation 10,000 times more intense than the radiation belts surrounding Earth. As the probe skimmed past the giant planet, it gained speed. Leaving Earth, Pioneer 10 was moving at 51,000 kilometers per hour. Departing Jupiter, it had more than doubled its speed. This gravitational slingshot effect made the Grand Tour possible. The Grand Tour craft, recently renamed Voyager 1 and 2, were due to be transferred to Cape Canaveral for launch integration when news of Jupiter's extreme radiation environment came through. The electron radiation at Jupiter had generated false commands within Pioneer 10. With the far more sophisticated Voyagers, this presented problems. Local supermarkets were stripped of their stocks of kitchen-grade aluminium foil, which was then used to shield critical cables. Without this last-minute alteration, electrical pressures of up to 40,000 volts would have been induced in the Voyager's subsystems as the craft passed Jupiter. Voyager 2 was launched in August 1977. Its trajectory meant that it could visit Jupiter, Saturn, Uranus, and Neptune. Voyager 1 left 16 days later. Its different, faster trajectory only allowed flybys of Jupiter and Saturn and various large moons. At the time, the Voyager spacecraft were the most sophisticated probes to be launched. Because they were to operate at huge distances from the Sun, solar panels could not be used as a power source. They were equipped with radioisotope thermoelectric generators, which use the heat from the decay of plutonium-238 to generate power. As Voyager 1 approached Jupiter in January 1979, it began sending image sequences that showed a complex and dynamic planet. The planet's giant red spot was revealed as a vast rotating storm. In 1665, Giovanni Cassini described a permanent spot on Jupiter which was regularly observed into the 1700s. It was not until the late 1800s that Jupiter's spot was described as red, and it's uncertain whether the historic observations of Jupiter's spot refer to the same feature or a phenomenon that regularly manifests in Jupiter's atmosphere. Voyager 1 made its closest approach early in March 1979. As the probe neared Jupiter, the activity at NASA's Jet Propulsion Laboratory became intense. This was the nature of the Voyager's flyby missions. There were long, quiet cruise phases between the planets, followed by brief periods when the flow of information from the craft overwhelmed researchers. One of the biggest contributions made by the Voyagers was the transformation in our understanding of the Galilean moons. Previously just dots of light, Jupiter's 4 largest moons were each distinct and completely different. The first surprise was the inner moon Io. It's a sulfurous yellow in appearance, and one particular long-duration exposure revealed an odd plume. Rather than being a cold, dead world, the gravitational squeezing Io receives from its giant neighbor heats the moon's interior. The plume was a volcanic eruption, ejecting material hundreds of kilometers above the surface. In July 1979, 3 months after Voyager 1 had moved beyond Jupiter, Voyager 2 made its closest approach. It was able to examine different moons more closely than its twin. Europa was the next surprise. It is highly reflective and has the smoothest surface of any body in the solar system. Further observation revealed pressure ridges reminiscent of polar ice flows on Earth. Europa is a frozen world, with a vast ocean beneath a thick crust of ice. Like Io, it is heated from within by tidal flexing. As Voyager 2 continued toward Saturn, planetary researchers were left with large amounts of raw data about Jupiter still to be processed. The Voyager missions left us with a basic view of the Jovian system, but they had raised more questions than they were able to answer. It would be more than 10 years before Jupiter received another visitor from Earth.
Ignition and liftoff of Discovery and the Ulysses spacecraft bound for the polar regions of the Sun.
In October 1990, the Space Shuttle Discovery lifted the European Ulysses spacecraft to low Earth orbit. From there, it was boosted on a mission to observe the Sun, but first, it would pass Jupiter. All the planets orbit the Sun in the same direction, in roughly the same plane. This is called the ecliptic, and it developed from the spinning disk of dust and gas that formed our solar system. The designers of the Ulysses spacecraft wanted to see the Sun from an orbit above its poles. Jupiter's extreme gravitation was used to bend the probe's flight path out of the ecliptic so it could make north-south orbits of the Sun. Ulysses was not the only probe to take advantage of Jupiter's gravity. Both the Cassini probe to Saturn, launched in 1997, and the New Horizons probe to Pluto, launched in 2006, were able to reduce their flight times by years with Jupiter flybys. These probes were able to make meaningful observations while passing the giant planet. In the clean rooms of the Jet Propulsion Laboratory, a new probe was taking shape. Galileo would be the first spacecraft to go into orbit around Jupiter. Its 4.8-meter antenna was folded like an umbrella, only to be deployed when safely on the way to Jupiter. Originally scheduled to launch in 1986, it sat in storage for years after the Space Shuttle Challenger exploded.
10, 9.
It launched aboard Space Shuttle Atlantis in October 1989.
4, 3, 2, 1. We have ignition and liftoff of Atlantis and the Galileo spacecraft bound for Jupiter.
New rules governing shuttle launches meant a change in the booster to push Galileo out of Earth orbit. The less powerful solid fuel upper stage, now stipulated, sent Galileo toward Venus for a gravity assist. The new flight path meant Galileo was traveling to a hotter part of the solar system. It was decided to keep the heat-sensitive antenna furled until after the spacecraft looped back past Earth. Galileo made 2 close passes of Earth, each time gaining more speed. Its first pass was in December 1990, more than a year after its launch. A further year on, when it passed Earth again, the high-gain antenna was only partially open. After months of trying different techniques to deploy the antenna, mission engineers concluded that long periods in storage had caused lubricant at the tips of the antenna's ribs to dissipate. Researchers would rely on Galileo's smaller antenna with data delivered at slower rates. During the cruise to Jupiter, Galileo encountered several asteroids. This is Ida, the first asteroid we've learnt of with its own moon, Dactyl. In July 1995, while it was still 6 months away from its closest encounter with Jupiter, Galileo ejected a small probe designed to enter the atmosphere and sample its chemical composition. The probe lasted for an hour in Jupiter's atmosphere. The data was relayed to Galileo and recorded for subsequent transmission back to Earth. Its analysis revealed hardly any water vapor, which was unexpected, and other elements, particularly helium, were detected at far lower levels than predicted. The probe experienced areas of extreme heat and cold, suggesting heat is being released from the planet's interior. Slightly more than an hour after transmission from the probe ceased, Galileo began its orbit insertion burn. Its engine had to operate for 49 minutes to put it into a highly elliptical equatorial orbit. But this orbit would be altered with another burn at its high point. Mission designers were acutely aware of the high radiation environment, and the second burn would lift Galileo above the extreme radiation at its closest approach. Galileo's initial orbit eventually delivered a close approach to Ganymede, Jupiter's largest moon. During this orbit, engineers were trying to understand damage to the spacecraft's vital tape recorder. Without its high-gain antenna, the recorder was essential for slow replay of data recorded during the brief, close encounters. It had been stuck in rewind for 15 hours, and tape had been degraded. Light-emitting diodes, key elements in the recorder's control system, had acquired radiation defects. The second orbit also passed Ganymede. Galileo discovered it's the only moon in the solar system with a significant magnetic field. It also has an ocean sandwiched between 2 layers of ice. Galileo's orbits would be slightly varied so that it could make close approaches to different Jovian moons. But the equatorial orbits needed to reach the moons also took the craft through hotspots in Jupiter's radiation belts. With the observations made by the Voyagers, the moon Europa was of particular interest to the Galileo team. Data from several instruments agreed that a salty ocean exists beneath Europa's surface ice. Later examination of the Galileo datasets revealed plasma wave and magnetic field information, showing that plumes of water vapor were erupting from cracks in the surface. Europa has more water than Earth, which makes it a possible home to life. Io was already known to have volcanic activity, but Galileo saw tides in the moon's solid surface of more than 100 meters. The temperatures generated by this gravitational distortion of Io make its numerous volcanoes hotter than anything found on Earth. During its 8 years at Jupiter, Galileo completed 35 orbits, filling out our limited picture of the Jovian system. This was never an easy mission. Galileo was a robust spacecraft, but the radiation environment stressed all the subsystems, and engineers were constantly having to find workarounds for the frequent breakdowns Galileo suffered. Instruments showed increased noise when near Jupiter, and current leakages caused by radiation led to several resets of the onboard computer, with crucial loss of data. Software changes enabled the computer to recognize these resets and to recover by itself. Information learned would lead to changes in the way the next Jupiter spacecraft was designed.
5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter.
In August 2011, Juno began a journey to Jupiter that would last almost 5 years. Its mission parameters would be very different to Galileo's. It would ignore the moons and focus exclusively on Jupiter.
Chamber pressures have plateaued.
Spacecraft design saw crucial electronics shielded within a thick titanium vault, and rather than a plutonium power source, Juno would rely on solar panels. The sun's intensity at Jupiter is roughly 5% of what it is at Earth, so the panels are huge. A shortage in stocks of plutonium-238 led to the change in power sources. Juno followed a looping orbit that took it beyond Mars before swooping back to Earth for a gravitational boost that added 14,000 kilometers per hour to its velocity, sending it on to Jupiter. Juno approached Jupiter on a path that took it above the planet's north pole. It was destined for a north-south orbit. This would see it pass beneath the severest sections of the planet's radiation belts that extend out from Jupiter's equator. 4 days before its closest approach, Mission Control sent a command that initiated the craft's autopilot. On July the 4th, 2016, Juno began an engine burn that would insert it into a 53-day orbit. 48 minutes later, Mission Control at JPL received tones verifying that Juno had started its deceleration maneuver. It was a tense 35-minute wait from the system's engineers before confirmation came through that Juno had performed exactly as intended. For the Juno scientists and engineers, it was a relief that things were going to plan. Juno is equipped with a suite of instruments capable of penetrating Jupiter's thick cloud. The polar orbit allows Juno to compile a three-dimensional map of the upper atmosphere, building a picture of the entire planet as it rotates. The images of Jupiter from this new perspective appeared to come from a different planet. Researchers were stunned. It was planned that Juno would only make 2 53-day orbits and then change to a series of 14-day orbits that would speed up the sampling rate. The spacecraft's main engine is fueled by hydrazine and nitrogen tetroxide, which ignite spontaneously when mixed. The propellant and oxidizer are forced out by a bladder of expanding helium. As Juno was finishing its second orbit, the helium valves were not responding correctly, so it was decided to maintain the original orbit. A mission extension has been granted to allow for the longer orbits Juno continues to follow. Within a day of the helium valve problem, Juno went into safe mode. All instruments went offline and data was lost. It appeared to be similar to the difficulties experienced by Galileo, but engineers traced the issue to a data transfer problem from one specific instrument, and the spacecraft remains healthy. Jupiter's axis is tilted at only 3 degrees, making even an oblique view of the poles near impossible until Juno arrived. When viewed in the infrared, researchers saw a complex arrangement of storms at both the poles. At the North Pole, a central vortex is surrounded by 8 anticyclones. At the South Pole, 5 anticyclones surround the central storm. Scientists do not understand why the storms, all rotating in the same direction, do not obliterate each other. On its 7th close pass of Jupiter, Juno flew directly over the giant red spot. Its microwave radiometer was able to map the heat distributions at varying levels down to 350 kilometers. The red spot is a giant storm, and Juno was able to see much higher temperatures at the deepest levels they could penetrate. With no geographic features, as on Earth, there is nothing on Jupiter against which storms can dissipate. The Great Red Spot remains firmly 22 degrees below the equator, yet it appears to have drifted around the planet at least 10 times since reliable observations began. Jupiter's magnetosphere is huge. It traps charged particles in bands stretching out to vast distances. This gives sensitive electronics on orbiting spacecraft like Juno big problems. It was assumed that Jupiter's magnetosphere was generated, like Earth's, by dynamo action, the convective movement of an electrically conductive fluid deep within. So far, results from Juno suggest that this is not the case. The lumpy nature of Jupiter's magnetic field points to an atmospheric source. The giant auroras at the poles also seem to come from a different mechanism than here on Earth. By focusing on the composition of the gas giant, researchers are hoping to gather clues about conditions at the formation of the solar system. While the Earth has been continuously changed by tectonic forces, it is thought that Jupiter remains very similar in composition to the cloud of gas and dust from which the solar system was formed. At the end of its mission, Juno will be sent on a collision course with Jupiter to avoid any possible contamination of the delicate moons. The next mission to the Jovian system will focus on Europa, as the most likely place after Earth to harbor some form of life. Known as Europa Clipper, it's scheduled to launch in 2022. Like Juno, it will be solar-powered, and its elliptical orbit of Jupiter will see it fly over Europa every 2 weeks. Early concepts for the mission called for the inclusion of a lander, but this idea was soon rejected as premature because more needs to be learned about the surface of the icy moon. Though Europa's ice crust is thought to be at least 19 kilometers thick, accurate measurements need to be made. If thin areas can be found, then future missions may be able to access the ocean that lies beneath. Concepts for under-ice explorers are in development, and we can expect other missions to focus on other moons. As the largest planet, Jupiter's influence on the rest of the solar system is profound. It has more than twice the mass of every other planet combined. All other planets' orbits are affected by Jupiter's gravitation. There is still much to learn about Jupiter.